Hi guys, so this video series is all designed to help with review for the AP 1 physics exam. Each lesson or video that we have, we'll go ahead and do little snippets on some particular topic, unit, or an area we want to discuss. Within this one, we also want to try to make each one of these videos like 15-20 minutes, so it just brings out basic ideas to help review main concepts to show us what's going on. This first one we're going to reference kinematics, not just one, but two-dimensional kinematics to show us all these individual ideas. So let's get started. The idea is that kinematics deals with things only moving without reference to forces. So we're just talking about things moving. So kinematics, we're just talking about some simple things. We're talking about velocity. Velocity being a change in position over change in time. Now with that being said, anything changing or moving through some type of space in some specific time interval. The greater that velocity is, we're covering more distance in a shorter time interval, basically. The other way we look at this is the idea of acceleration. Acceleration is change in velocity over change in time. We need to reference back to old ideas. Acceleration can happen if things speed up, if they slow down, or change direction. The thing that cause things to accelerate is force. That will be in a future video, but we know that idea of things we've already kind of talked about. Now, if we have things accelerating, and it's going to do so uniformly, we can use some cool things. That's where we get our kinematic equations. That's where we get those funky things up there. That our final velocity is the initial velocity plus acceleration times time. Now, that looks a little bit weird, as well as x to x naught t plus 1/2 axt squared. In this case, we're saying that's our final velocity, that's the initial, that's acceleration, and that is time. Now, in our next one, we find this is the final position, that's the initial position, that's the initial velocity, that's time, that's acceleration, that's time. In that second equation, you have to do some weird stuff if you're asked to find the final time. Because you notice you'd actually have to solve that as a quadratic equation in order to do so. I don't think that you have to completely go through that whole measurement or all that whole work on the AP exam. That's something to keep in mind. Okay, b squared is b naught squared plus 2x minus x naught. We find this shows an exponential relationship when doing velocity, accelerations, and some different ideas. So first thing we want to reference is what does this stuff mean in terms of just straight line motion stuff. Then we want to talk about in terms of two-dimensional, meaning straight that way and that way. So what do we mean by that? If we have something that has an acceleration, let's just say it's moving with a is equal to 0. Now, in this case, we're going to go ahead and say that that's supposed to be a car. Okay, it's supposed to be a car like that. Okay, just for instance, that's it's moving the constant with some velocity, okay, not equal to 0, and it has an acceleration equal to 0. That means it's going to be moving this way, and we notice, in this case, equal intervals as we see here. If a is not 0, okay, and the velocity here is positive, we find that it's going that way, right? And let's say, let's even make it's a positive acceleration. It's going that way, and if acceleration is that way and velocity is that way, that means it's going to go ahead and cover a larger distance this way. I did not help show that very well, right? To show that it would be increasing. Okay. I'm trying to show the idea that this distance is increasing over time. Say it's accelerating that way. We cover more distance per time as it's going in and going that way. Now, other weird things happen if we have a velocity this way, we'll make that positive again, and have an acceleration opposite that direction. So that means it can be going this way, but it can actually be going ahead and slowing down. The size of the object shouldn't be changing, but it is. Okay, it's slowing down, and then it's going to go ahead and go the opposite way. Actually speeding up that way. You say, well, that seems kind of weird. Something to slow down, stop, and start accelerating that way. Well, on a one-dimensional plane like this, it seems a little bit weird, but the way that we can see this more evident is we take something and we toss it up in the air. If I take an object and I throw it directly up in the air, we're then not talking about the idea of just something accelerating, we're then talking about free fall stuff. If I take a ball and I toss it up in the air vertically, it's going to be here, here, and here, and here. We want to look at where it's located over some specific time intervals. Notice it's covering a whole bunch of velocity, it's covering a whole bunch of distance here, it's a high velocity here, then it's decreasing. On the way back down, it's going to be speeding back up. You realize that if we were to show velocity vectors or the arrows to denote what's going on, I have a velocity here, and then as it goes up, that velocity is indeed decreasing. On the way back down, it's increasing. It's increasing the same amount down as it did slowing down on the way back up. Again, it's slowing down just as much as it speeds back up on the way back down. Crazy. The entire time, that acceleration is equal to 980 meters per second squared. And if I pick my coordinate system to be downward, that means that that actually gives me a negative value. Crazy stuff. Now, the beauty of that is I can use G as A in any one of those kinematic equations. So no matter what I'm doing, I can force that to be that. Now, this only works on Earth. If this was the moon or some other planet, that gravitational acceleration would indeed be different, but that's okay. Now, a point that I'm trying to reference here, and it comes up as a big conceptual question, is at the top here, yes, velocity is equal to 0, but it is indeed still accelerating. Remember, velocity does not affect acceleration. Velocity does not affect acceleration. As position does not affect velocity. Now, in referencing these ideas, we can also talk about graphs of relative motion. Now, what do we mean by that? We can talk about distance time graphs, and we can talk about velocity time graphs. Now, in looking at those different things, if it was to say that I had something stationary. Now, if you want to go ahead and take a moment to go ahead and kind of pause the video to try to think about what's going to happen in each one of these situations, you can feel free to do so. Now, in the first one, we can see a distance versus time graph and a velocity versus time graph. In the first case, if something was stationary at some point of 1, what would it look like? Okay, it's going to be like this. Like that. Distance constant, and that's going to be constant like that, right? At that same velocity. Now, let's say it's moving with some velocity of like 2 or 3 meters per second. Something constant. What would that look like? Well, that's a little bit different. In that case, that means it's covering a constant amount of distance per time interval. We get something like this. Cool. If we were to look at the velocity versus time graph, what would that look like? Well, that's going to be a constant velocity, something like that. If we were to say that this thing starts from rest, but is increasing in its rate in which it's covering a distance, meaning it's accelerating, what would that look like? Well, then we'd go ahead and see something a little bit different. We'd see some type of exponential trend, something like that. Weird. What would the velocity time graph look like? Something like that. As long as it's a uniform acceleration. So as long as it's a uniform acceleration. So on a distance time graph, the slope is velocity. Distance versus time graph, slope is velocity. On velocity time graph, slope is acceleration. Notice in this case, we have a constant slope, constant acceleration. If that was wavy or doing all kinds of weird stuff, simple harmonic stuff, waves, sinusoidal things, that would mean that, oh yeah, we have a changing acceleration. That's what that could be referencing. Now, the other thing we want to look at with this is something that pops up a bit, is not just looking at velocity acceleration, but dealing with distance. So you said, well, how can I look at these ideas and come up with distance? Well, if I was actually trying to look at this idea for this second line that I drew here and say, okay, yeah, I know it has an increasing velocity. Yes, I know something happens in terms of time. Well, I can't really figure out what's going on here. But how can you find out how much distance that thing would be covering? If I look at this, the area underneath.
At this time, breakfast is over. All high honor students should be reporting back to class. Again, our breakfast is over. All high honor students should be returning back to class. Thank you.
The area underneath, that gives us our distance. See, how did I come up with that? Well, velocity is your distance over time. So velocity times time, so velocity times time would be equal to our distance. That makes kind of sense based upon old ideas as we see here. Now, the other part we want to deal with this thing is not just in terms of distance, in terms of velocity graphs, but we also want to think to ourselves, well, what does this stuff really mean? How can we see how these things could be exhibited? What does this stuff mean for us? Well, we may be asked to look at some of these different graphs or some different situations and say to yourself, well, how could you describe these things? So at the end of each one of these videos, I want to try to do a little type of free response style questions to kind of make you think a little bit. So if you were to think to ourselves, if I have a car that's here, okay, and it's moving this way, and has some acceleration that way, okay, and it it has some velocity also directed that way. If I make this point A, if I make this point B, if I make that point C, excuse me, if it's accelerating that way, okay, point A, point B, point C, at what point will velocity be equal to 1/2 the final? Now, I'm saying the final velocity when it's here, okay? So when will the velocity be 1/2 the final? So when would that will occur? Now, it may appear that be someplace near B, right? No, it's actually between A and B. Why is that so? Why is that so? Because it's covering more distance per time interval as it starts increasing in its speed and moving to the right. Weird. The other part we want to reference is what happens to something as it falls. Now, as it falls, what happens to the distance proportionality? So, as something falls, it does this. Well, we see that it's going to go and be increasing distance. We talked about this idea a little bit before in class, but we were to look at the drops on a faucet, something like that. What happens to those distance between those drops? It increases because the one that's been dropped before is actually going to be going faster than the one above it. Now, does that mean that they have the same velocity? No. The one below it will be going faster than the one above. Do they have the same accelerations? Yes. They have the same accelerations, but they have different velocities. They're also covering different distances per time intervals. Now, we also want to focus within this short video the idea of two-dimensional kinematics. So we also want to focus on the idea of two-dimensional kinematics. What do we mean by that? Motion this way and this way. That means we can see things being thrown through the air or the idea of relative velocity. Now, what do we mean by those things? If we have something shot like this through the air, and it's like this. Now, if it's being shot through the air like that, we say, okay, it's flying through the air, does some cool stuff, yeah, whatever, lands, hits something, we don't really care. But what we can say is, if it's shot at some angle theta, and I know this velocity here, I know that Vx, in terms of what I have here, will be V times cosine theta. This is old school stuff, breaking things up into components. In this component, Vy would be equal to V times sine theta. Crazy things. Now what can I do with that stuff? I can use my kinematics that we see over there to describe what's going on. I can use any one of these components to compare how this thing is flying through the air, find final velocities, to show those basic ideas. Yes, we could do a lot of problems with numbers with this, but our big focus is not saying, well, not complete numbers, but how can we go ahead and just express what's going on? Now, what does that mean in terms of things being shot like this? Well, this angle, something being shot like this, can ultimately determine range. It's a function of its components. Now, some things that we should realize when something's shot like this is, in the x direction, acceleration is 0. It no longer accelerates that way. But we do know it slows down going up and speeds up coming back down. There are ay, and if I define right and up as positive, ay would be equal to -8, 98 meters per second squared. Crazy stuff. Then we can go ahead and look at those individual components as we see there. Now, a big part to determine some different things going on. At this point here, something unique happens. The velocity in the y, not the velocity completely, the velocity in the y is equal to 0 at that point. Now we can use that, if I can find the time to get that, by using anywhere in kinematics, I can go ahead and multiply it by 2 to get the whole time if it's going to land like that, or I can find the individual components and see what's going on. Now the other part that goes along a lot with two-dimensional kinematics is not just this in terms of things flying through the air, but also something called relative motion. Now, this comes up, a big way to look at this is if there's like a river like this. If we have a river and it's moving with some speed, okay, so that's the velocity of the river that way, okay, and I have a boat, and that boat's attempting to cross, and it has some velocity in in that direction. Okay? Now, if I have it that that boat has some velocity, so we call it v sub b for velocity of the boat, and v sub r for the velocity of the river. Now, this turns into a two-dimensional problem because we have velocity both this way and this way. Ultimately, if this tried to go straight across with velocity that way, it would end up being done that way. Now, in most problems like this, you're assuming that neither the river nor the boat accelerate. So both have accelerations of 0. So what does that mean for us? Makes things a little bit easier. But they could make a crazy AP question, or they could have an acceleration of the boat, which wouldn't be that bad, because you just simply apply acceleration in this frame. Now, if we were to go and say, okay, well, if I was to find out how long, so if this was distance x, okay, we say, okay, how long is it going to take for it to go and cross here? Honestly, the speed of the river has nothing to do with how long it's going to take for it to cross here. That speed of the river will affect how it's going to end up down here. Just like how we dealt with problems before something horizontally launched. If something's horizontally launched, we know the time for it to fall this way and the time for it to travel out that way are indeed the same. And that horizontal speed does not affect the vertical drop. Here, this horizontal, or this velocity this way across the river is not affected in terms of the time to cross, in terms of the velocity of the river that way. So, a question that you could be asked of this is, how could you, or how could this be determined to make sure that you want to rearrange this? Okay. So we have our boat on the shore now to determine this idea. If we were to look at this thing and say, okay, if that's velocity of the river, okay, and our boat can go ahead at some speed v boat. Okay? Okay. If we were to determine the speed for it to go across, you say, how could we deal with that idea? Now, if we don't just go straight across, things get a little bit more interesting. So what I'm saying is, if I have the boat like this, and it's not aimed straight across or down, it's now aimed like this. It's now aimed like that. What I'd like you to do is to try to think about how you determine how long it would take for it to go ahead and move to the other side. Okay, so how long would it take for it to go to the other side? Ultimately, when looking at this thing, you'd have to think about one part that I don't have included here, and it deals with the angle theta. Now, in terms of a conceptual idea, you can just say, okay, if I have this equal to that in that direction, those two things cancel out, that's going to be my speed across, right? If those two things are equal, and we have that going on, it's just actually going to do this, which should be kind of weird. Just do that, fair across. Now the other part to look at this is, well, what if this is greater than this? That means it's going to end up upstream. If this is less than this, it's going to end up downstream. That component, that's what's going to allow it to go ahead and move across. Guys, that's what I have today. We're dealing with one-dimensional, two-dimensional kinematics. As always, you can feel free to email, ask me questions. Have a great day.